Welcome to section 8.3. Let's look at functions today. Students will be able to understand and explain the following. The concept of a function, including the domain and the range. And we'll look at different representations of functions. One can think of a function as a rule whereby when one value is given, the function or rule specifies a resulting value. A function is like a machine. You put something into the machine known as the input, and the machine's going to do some calculations, and it's going to give you an output. In general, we plug in values into the function, and the function does some calculations and gives you one output for that associated input. For each input, we're going to get exactly one output from it. That's a function. In example 7, I want to guess the teacher's rule for the following response. When a student says 1, the teacher responds 3. When the student responds 0, the teacher's answer is 0. When the student says 4, the teacher says 12. And finally, when the student says 10, the teacher responds with a 30. So what rule allows us to determine how the teacher will respond? Take some time and try part A and part B on your own. Figure out the formula or rule that we need to perform to the student's number to get what the teacher is going to respond. Let's work on it together now. In part A, notice if we take the number 1 and multiply it by 3, we do get 3. If I multiply 0 times 3, I get a 0. 4 times 3 gives me 12. And 10 times 3 gives me 30. So that's our rule. Our rule is we're going to multiply our number by 3. So our rule for part A is to multiply by 3. Now, how do we write this as an equation? How do we write this as an equation? Well, this is the same as taking our number n and multiplying it by 3. So that's our formula. It's 3n. In part B, how do we get a 5? Well, I need to multiply 2 times 2, then add 1 to it to get a 5. 3 times 2 plus 1 also gives me a 7. 5 times 2 is 10. Add 1 more, I get an 11. And for the last one, if I multiply that by 2 and add 1 to it, I do get 21. So the rule for part B is to double the number and then add 1 to it. Now, how do I write this in terms of an expression? Well, I need to take n and double it. That means I will take n and multiply it times 2 and then add a 1. So these are the formulas for our teacher responses. For part A, I need to triple our number or multiply by 3. For part B, I will need to double our number, then add 1 to it. In part C, again, we're going to guess the teacher's rule for the following responses. I want you to pause the video and try this one on your own. Figure out a rule on what to do to get to the teacher's response. In part C, if the number is even, we are going to give a 0 as the answer. 2 goes to 0, 4 goes to 0. All of the evens goes to 0. But for the odd numbers, it seems like the odds all go to 1. So in this case, our rule is send all of the evens to the number 0 and send all the odds to the number 1. In part D, please pause the video again and try it on your own. This one's going to be a challenge. Let's go over the answer for part D. For the first row, I'm going to take the 4 squared and then add a 2. 4 squared is 16, and then we'll add 2 to that 16. 16 plus 2 is 18. So that works out for the first row. For the second one, let's square 5 and add 2 to it. We know 5 squared is 25, and 25 plus 2 is 27. So this appears to be the correct process. So let's try the third and fourth rows. 7 squared plus 2, that's 49 plus 2, and that is 51. And for the last row, we have 12 squared plus 2, that's equal to 144 plus 2, which reduces to 146. So this is the correct process for each of the rows. So let's come up with our formula. We take the number n, and we have to square it, then add 2. So that's going to be n squared plus 2. That's the correct expression for this problem. It's n squared plus 2. Another way to think of a function is a machine. The machine has an input and output. Here we're inputting a 6 into the machine, and the machine does a calculation. It squares the input, and the output is 36. In function notation, it would be written like this. F of x is equal to x squared. The x here is the input, and the output is our answer, x squared. So if I put a 6 into the function, 6 would be the input, and then we're going to square it, and of course 6 squared is 36, that's the output. So please be familiar with function notation. This is pronounced f of 6. It is not f times 6. This is function notation. In example 8, for the function named f, what would happen if the numbers 0, 1, 3, 4, and 6 are inputs for the machine? If I were to input 4, the machine would add a 3 to it, and we would get f of 4 is equal to 7. So let's construct a table of this function. If x was 0, we plug in a 0, add 3 to it, we get a 3. If x was 1, we add a 3 to a 1, we get 4. We add a 3 to a 3, we get 6. And if the input was 4, we add 3 to it, we get a 7. If the input was a 6, we add 3 to it, we get a 9. So our x values is the input, and x plus 3 is our output. The x is the input, and the x plus 3, that's our output. We can write an equation to depict the rule in the previous example. If the input is x, the output is x plus 3. That is, in function notation, f of x is equal to x plus 3. What that means is I can write f of 0 in function notation, and that means replace that x with a 0 and add 3 to it. So f of 0 is equal to 3. F of 1 means plug in a 1 into our function, replace that x with a 1. So 1 plus 3 equals 4. F of 3 means replace the x with a 3, then add 3 to it, we get 6. F of 4, again, all I have to do is replace the x with a 4, add 3 to it, and we get a 7. So you get the idea. Function notation is just another way to represent our machine. We plug in our inputs, and we get outputs from the machine or the function. Let's look at another function, f of x equals x squared minus 3. So this function takes our number, squares it, and then we have to subtract 3 from it. So I want you to take some time and figure out what f of 5 is. What is f of 5? And what is f of 0? Let's try it together now. F of 5 means I have to plug in a 5 into the x. So that is equivalent to 5 squared minus 3. 5 squared is 25, and then I have to subtract 3 from it. So f of 5 is equivalent to 22. For f of 0, that means I must plug in a 0 into the x, and so we have 0 squared minus 3, and 0 squared is just 0. 0 minus 3 is negative 3. This is just a few examples related to evaluating functions. Let's look at the definition of a function. A function from set A to set B is a correspondence from A to B in which each element of A is paired with one and only one element of B. The domain is equal to the set of A, the set of all possible inputs. So the set of all possible inputs is known as the domain. For the range, that's equivalent to set B, which is the set of all possible outputs. All of the possible outputs is the range. Is this input-output machine a function machine? For any natural number input x, the machine outputs a number that is less than x. So think about it for a moment. If I put a number x, it's going to pop out a number that is less than x. Is this a function? Well, let's go back to our definition. Our definition says there is a correspondence from A to B in which each element of A is paired with one and only one element of B. That's very important. So we're saying that if I put a number x, I can only get one output that is related to it. So is this machine a function or not? Well, it is not a function. No, for example, if you input the number 10, the machine may output a 9, since 9 is less than 10. If you input a 10 again, the machine may output a 3, and since 3 is less than 10, it would possibly give you two different outputs. This is not a function machine because the same input may give different outputs. Remember, we can only have one output for each input. Example 9. A bicycle manufacturer incurs a daily fixed cost of $1,400 for overhead expenses and a cost of $500 per bike manufactured. In part A, find the cost function C of x of manufacturing x bikes in a day. Since the cost of producing a single bike is $500, the cost of producing x bikes is $500x. Because of the fixed cost of $1,400 per day, the total cost C of x in dollars of producing x bikes in a given day is given by the formula C of x equals 500x plus $1,400. We're adding the cost of each bike plus the overhead cost of $1,400. So this is our cost function for manufacturing those bikes in a given day. In part B, if the manufacturer sells each bike for $700 and the profit or loss in producing and selling X bikes in a day is given by the function P of X, find P of X in terms of X. To find P of X, we're going to start off with 700X. That's the amount of revenue generated per bike. It's $700 for each bike. Then we're going to subtract our cost function, C of x. Recall our cost function is equivalent to 200x plus 1,400. But you want to be careful when you're subtracting the cost function. Make sure you put parentheses around it because we're subtracting the whole cost. Let's distribute the negative sign throughout our expression. This simplifies to 700x minus 200x minus 1,400. We could collect like terms. 700x minus 200x is 500x minus 1,400. This is our profit function. P of x equals 500x minus 1,400. In part C, we want to find the break-even point, that is the number of bikes X produced and sold at which break-even occurs. To break even means to make neither a profit nor a loss. We need to find the number of bikes X to be produced so that P of X is equal to 0. Recall our function P of X was equal to 500x minus 1,400. So we'll just replace P of X with 0. That means 0 equals 500x minus 1,400. I could add 1,400 to both sides. This gives me 500x is equal to 1,400. And then we could divide both sides by 500. And so x is equal to 7. What does that imply? Well, that implies we need to sell 7 bikes to break even. I need to sell 7 bikes to break even. Arrow diagrams can be used to determine whether a correspondence represents a function or not. For example, if we have this arrow diagram, a 0 gets sent to a 1, a 1 gets sent to a 2, a 2 gets sent to a 4, and a 3 gets sent to the 3. Is this a function or not? Well, we'll look at each input. It's associated with only one output, so this must be a function. Let's look at another arrow diagram. Is this a function or not? A 0 gets sent to a 1, a 1 gets sent to a 4, a 2 gets sent to a 4, a 3 gets sent to a 4, and a 10. This is not a function because the input 3 is associated with two outputs 4 and 10, so this cannot be a function. Remember, to be a function, for each input there's exactly one output for it. In example 10, which, if any of the figures exhibit a function from A to B? If a correspondence is a function from A to B, then I want you to also find the range of the function. Let's look at our first diagram. 1 gets sent to 2 and 1 gets sent to 4. So we have one input that goes to two separate outputs. Automatically, this is not a function. One input goes to two outputs. This is not a function. In the next diagram, we have A goes to 1, C goes to 2, but B has nowhere to go. Remember, to be a function, for each input, there's exactly one output. So in this case, B does not have anywhere to go, so it is not a function. In the next graph, X gets sent to A, Y gets sent to C, and Z gets sent to B. For each input, there's exactly one output, so this is a function. And the range of this function is A, B, C only. For each input, the only outputs are A, B, and C, so the range would be A, B, and C. For the domain would be the inputs X, Y, and Z. John goes to Brown, Mike goes to Smith, Joanne goes to Brown, and Sue goes to Doe. Is this a function? Yes, it is. For each input, there's only one output. For each input, there's only one output. There might be two inputs that goes to the same output, but they only get one output. So this is a function. A function is like a vending machine. I can go buy a Pepsi, and your friend could go buy a Pepsi. That's okay. It's a function. We can both get the same drink. But a person cannot put $1 and expect 2 drinks out of it. That is not a function. So let's look at the range. The range would be Brown, Smith, and Doe, all of the outputs. And of course, the domain of this function would be all of the individuals, John, Mike, Joanne, and Sue. That would be the domain of this function. 0 gets sent to 1, 1 gets sent to 4, 2 gets sent to 7, 3 gets sent to 10. This is clearly a function. For each input, there's only one output. This is a function. And the range is 1, 4, 7, 10. And of course, the domain for this function is all of the inputs. The domain would be 0, 1, 2, and 3. The L&B lawn service distributes the following fee schedule to their customers. It gives the price for mowing large lots given the number of acres in the lot. So we have the number of acres here represented by a table, and we could also translate it as an ordered pair. The number of acres, that's equivalent to our x coordinate, and the total price is equivalent to our y coordinate. So we can translate this as an ordered where the x represents our inputs and the y represents our outputs. So here's our ordered pair selection here, 1, 50, 2, 85, and so on. In example 11, which of the following sets of ordered pairs represents functions? If a set represents a function, give its domain and range if it does not explain why. In this example, I can draw an arrow diagram. 1 gets sent to 2, and 1 gets sent to 3. 2 gets sent to 3, and 3 gets sent to 4. So this does not represent a function. The reason it does not represent a function is we have the input 1 goes to 2 outputs. This is not a function because the input 1 has 2 different outputs. In part B, we have 1 goes to 1/2, 2 goes to 1/3, 3 goes to 1/4, and 4 goes to 1/5. It appears that for each of these inputs, we only have one output. For each of the inputs, we only have one output. So this is definitely a function. This is a function, and the domain is the set of the inputs, which is 1, 2, 3, 4. The range would be all of the outputs, which is 1/2, 1/3, 1/4, and 1/5. In part C, 1 goes to 0, 2 goes to 0, 3 goes to 0, 4 goes to 4. Is this a function? Well, yes, it is a function. A lot of people might get the same item, but nobody got 2 items or 2 outputs, so this is definitely a function. It is a function. The domain is 1, 2, 3, 4, the set of all inputs or x values, and the range, we only have 2 possibilities for the range. You can only get an output of 0 or 4. Graphs are probably the most common known ways of representing functions. Here we have the graph for the L&B lawn service. And so you can see each of the ordered pairs is mapped on the chart. In example 12, explain why a telephone company would not set rates for telephone calls as depicted on the graph. So look at this graph carefully. I want you to figure out why a telephone company would not set the rates based on this graph. The graph does not depict a function. If you look carefully, the graph does not depict a function. For example, a customer could be charged either 50 cents or 85 cents for a 2-minute call. Thus, not every input has a unique output. If you look at the 2-minute phone call, we can be charged 50 cents or we could be charged 85 cents. There is 2 outputs for this input, so this is not a function and therefore would be confusing to our customers. And so we cannot use the graph to set our call rates. Let's go over composition of functions now. If 2 is entered in the top machine, then we have f of 2 is a 6. Now we can take that 6 and then we can enter it into the second machine. In the second machine, it would give us a 12 as the output. For a composition of function, all we're doing is we're taking the output from one machine and we're plugging it into the input of another machine and seeing what new output we actually get. This illustrates composition of functions. Note the range of f is the domain of g. In example 15, if f of x equals 2x plus 3 and g of x equals x minus 3, let's find the following. F of g of 3. What this means is I need to figure out what g of 3 is first, then plug that into the function f. So we're looking for f of g of 3. We're going to have to evaluate g of 3 first. G of 3 means plug in a 3 into the x. That's 3 minus 3, which is equal to 0. So I know I need to plug in a 0 for g of 3. This is equivalent to f of 0. F of 0 means plug in a 0 for the function f. So we have 2 times 0 plus 3, and this simplifies to 3. So our first solution for part A is 3. In part B, I want to find g of f of 3, which means we'll plug in a 3 into the f, and then figure out what that is, and then we'll plug that into g. We are going to find g of f of 3. So let's figure out f of 3 first. We'll start with the inside. F of 3 is 2 times 3 plus 3, so that's 6 plus 3, and that's equivalent to 9. So we'll take this 9 and we'll plug it into the function for g. We are looking for g of 9. We'll plug in the 9 for the g function. That's 9 minus 3, and so 9 minus 3 gives us 6. And that's our solution for part B. In part C, let's find f of g of x. Again, this is equivalent to f of g of x. What that means is the entire function g, which is x minus 3, goes into the x of the function f. So I'm going to plug in x minus 3 into the function f. That's 2 times x minus 3 plus 3. And so we could simplify. That's going to reduce this to 2x minus 6 plus 3. And that simplifies to 2x minus 3. So this is f of g of x. In part D, let's do the opposite. Let's find g of f of x. This time, the entire function f goes inside the function g. So this goes into this time. So that means I'm going to write 2x plus 3. That's going to go in the x, and then we have to subtract 3 from it. So this simplifies to 2x. In part C, I want you to try it on your own. Pause the video and do part C. Okay, let's do it together now. I'm going to find f of g of x. That means g is going inside f. We'll take the x minus 3 and it's going to go inside that x. So this is equivalent to 2 times x minus 3 squared. Now when you square this, you have to FOIL it out. This is equivalent to 2 times x minus 3 times another x minus 3. So be careful, you have to FOIL this out. So let's FOIL it out. X times x is x squared. X times negative 3 is negative 3x. Negative 3 times x is negative 3x. Negative 3 times negative 3 is a positive 9, but remember there's still a 2 in the front, so we'll have to distribute that 2. But let's simplify the inside first. This simplifies to x squared minus 6x plus 9, and now we can finally distribute that 2 throughout. So our solution is 2x squared minus 12x plus 18.